Integration by parts is a method for evaluating some integrals. To describe this method, let's say that we have two differentiable functions u and v, and consider the product u times v. This is also a differentiable function, and we can compute derivative of this function using the product rule. So it's going to be derivative of the first function times v, and then plus, we take the first function times derivative of the second function. When we integrate both sides of this equation, then on the left-hand side we get u times v, because essentially integration cancels differentiation. And then on the right-hand side we get integral of the first function, and then plus integral of the second function. And essentially this is the formula for integration by parts. We can rewrite this formula in the following way. We can take this integral u times v prime, so that's equal to the product u times v, and then minus the second integral. And we'll be using this formula in the following example. To evaluate this integral by parts, we'll need to identify the part that we'll be taking derivative of, that's this part, and the part that we'll be taking antiderivative of, that's this one. So in this example, u is going to be the function x, and v prime is going to be the cosine function. Then derivative of u is 1, and antiderivative of cosine is the function sine x. So this integral is equal to u times v, so x times sine x, and then minus the integral of u prime times v, so 1 times sine x, so sine x dx. This is easy to evaluate this integral, so we have x sine x, minus and minus, so plus cosine x, and then plus c. To integrate the logarithmic function ln of x, notice that we can take this function and multiply it by 1. It doesn't change the function, so the integral of the function ln of x is exactly the same as the integral of the product. And then we can integrate this by parts, and this is the part u, and this is the part v prime. So u is the logarithmic function ln of x, and v prime is the constant function 1. So we know derivative of this function is 1 over x, and antiderivative of 1 is x. So this integral is going to be equal u times v, which is x times the ln function, and then we'll have minus the integral of u prime times v, but it's 1 over x times x, so it's 1 dx. Simple function to integrate, so we have x times ln of x minus x and then plus c. We'll use integration by parts 2 times to integrate the function x squared times the exponential function. So let u be the polynomial x squared, and let v prime to be the exponential function e to the x. Then derivative of u is 2x, and antiderivative of the exponential function is the function itself, e to the x. So this integral is going to be equal to u times v, so we'll have x squared times the exponential function e to the x, and then minus the integral of u prime times v. So 2 is a constant, we can pull it outside, so 2 times x, and then the exponential function e to the x dx. And this integral will evaluate this integral also by parts. So we'll let u to be x, the function x. So u is the function x, and v prime is going to be the exponential function again. So v prime is again the exponential function e to the x. Then derivative of u is 1. This is the constant function 1, and antiderivative of the exponential function is the function itself. So we'll have that this is equal to x squared times the exponential function e to the x minus 2 times, and this integral will be evaluating by parts. So it's u times v, so we'll have x times e to the x, and then minus the integral of u prime times v, which is 1 times the exponential function, which is the exponential function itself. So this is equal to the polynomial x squared and the exponential function e to the x minus 2 times x times the exponential function e to the x, and minus, so plus 2 times the integral of the exponential function, which is the exponential function itself, and then plus c. Here's another example. To evaluate this integral, let u be the exponential function e to the x, and let v prime be the trigonometric function sine x. Then u prime is the same function e to the x, and antiderivative of sine is negative cosine x. Then this integral is going to be equal u times v, which is negative e to the x times cosine x, and then minus the integral of exponential function times negative cosine, so it's going to be positive e to the x and cosine x dx. And we'll integrate this integral also by parts. So to integrate this, let u be again the exponential function e to the x, and let v prime be the cosine function now. So v prime is going to be cosine x, then u prime is the same function, and antiderivative of cosine is the function sine x. So we'll have that this is equal negative the exponential function e to the x times cosine, and then plus, well, this integral, which will be integrating by parts. So this is going to be equal u times v, which is the exponential function times sine x, and then we'll have minus integral of u prime times v. So e to the x times sine x dx. So now we have that the initially given integral, this one, is, so let's write this again. So this integral was e to the x, then sine x dx. This integral is equal to, well, this is the right hand side of our equation, so let's write this down again. And this is equal to e to the x. We can factor the e to the x, and we'll have, first of all, sine x, and then minus cosine x, minus cosine x, and then minus this integral. So minus integral of this function e to the x sine x dx. So now this on the right hand side, this integral on the right hand side is exactly the same as the one on the left hand side. So we have two of those integrals, e to the x sine x dx, and that's equal to, well, the exponential function e to the x times this difference, sine minus cosine. And last thing to do is divide both sides of this equation by 2. When we do so, then we'll get exactly the integral that we wanted to compute, which is 1/2 times the exponential function and then times the difference, sine x minus cosine, and then plus some constant c.